Hello everyone, and thank you for sticking around for my talk. I am Zachariah Peterson. I run my own company called Northwest Engineering Solutions, but you probably know me better as Altium's technical consultant. I'd also like to thank all of the other great presenters that we have here at EDICON. Today I'll be talking about some of the PCB design and simulation challenges present in 224 gigabit per second interconnects using Altium and Ansys. I will let anybody who wants to learn more about me and read my bio do so from the on-demand presentation. So we've got quite a bit to cover, so I'm just going to go ahead and jump in. First, let's take a quick look at an overview of 224 gigabit per second interconnects. So 224G is a doubling of the data rate from 112G. Prior work in this area looked at achieving this doubling of the data rate using various modulation options, such as PAM6 or PAM8. And this was actually mentioned in a Signal Integrity Journal article by Kathy Liu that was published in 2021. Currently, the data rate doubling that we see employs pulse amplitude modulation with 4 levels, or PAM4 modulation. This sets the Nyquist frequency to 56 gigahertz, and then that gives us a 112 gigabaud bit stream. When we look at the eye diagrams, we can start to see some of the signal integrity challenges that might arise in these channels. So when we look at the bottom left, we see a 2-level eye diagram, and then on the right is the same channel, but with a 4-level eye diagram. Obviously, the first thing you notice is, of course, the smaller eye opening. Once you have more noise, more ISI, more reflections and crosstalk, you then are at risk of closing that eye, and that makes it more difficult for the receiver to recover the signal levels in this bit stream. So we need to design these interconnects to prevent that eye closure. That requires reducing loss and ensuring impedance matching, so low return loss, up to at least 56 gigahertz in these channels. So 56 gigahertz is, I guess you could say, the magic frequency we need to target, and really we're targeting everything from DC up to 56 gigahertz. So this creates signal integrity challenges in 3 broad areas. So the first area is in connector and cable products. Now, I am not a connector and cable expert, so I don't really want to comment on the SI challenges in these products. I will leave that to the connector and cable experts if there are any around. However, on the PCB, when we start to look at the PCB and how we are routing signals between different elements on the PCB, we see several areas where there are SI challenges that will arise at 56 gigahertz. So the first is pad design and via design. The second is in our traces, and traces are, of course, lossy, both in terms of copper loss and dielectric loss, and so they generally start to get shorter. Then material selection will also affect interconnects. It not only affects the loss, but also things like crosstalk. So the folks in the packaging world already know this quite well. Then the packaging itself, which is the interface between what is going on the die and then the PCB. The packaging also matters and creates its own set of SI challenges. So one example that I've highlighted here is, of course, ball pitch on BGA packages. There's also the need for bump-to-bump simulation capabilities. And then equalization schemes also are quite important for recovering data from a bit stream. So in this presentation, I will primarily focus on the PCB. However, I will touch on packaging because there is a bit of overlap between the SI challenges on the PCB and in packaging. So the physical architecture supporting 224G PAM4 channels, there are 3 options, and I've shown these 3 options here. So in the top, we have what is, I guess you could say, closely resembling the traditional architecture, where you have a BGA with a processor that's placed onto a PCB, and then there's an I/O connector module on the right side of the board. I've drawn it hanging over the edge because they often are hanging over the edge, and then you have traces on the PCB routing in between these. So those traces can be rather long, and even if you have perfect impedance matching at the ends, the losses in these traces will be insertion loss dominated. So this is simply because the traces are long enough to have noticeable insertion loss. Then, once you start to realize that the insertion loss is much more problematic at 56 gigahertz, you have one option, which is to move the connector closer to the chip. And so this gives us near chip connectors shown in the middle row. So near chip, of course, as its name suggests, is placed near the chip. And what that does is it reduces the trace length required in order to route between these two elements. So now the loss mechanism in these interconnects switches from insertion loss dominated to return loss dominated. And then this requires very good impedance matching at each end of the interconnect, both under the BGA and under the connector. Next, we have on-package connectors. So this is really the best case because it eliminates some of these more difficult to design physical interconnects. This is another instance where I will defer to the connector manufacturers because they're really the experts in this. So I'm going to stick mostly to the PCB cases that we have here up top. So let's look a little deeper at the PCB cases. So if we're looking inside or in the interior of a PCB, we really have a lot of parameters that determine the signal integrity performance of these structures in PAM4 channels or in 224G PAM4 channels. So first, when you get up to 56 gigahertz, you could have shorter interconnects that do have a lot of insertion loss depending on the materials you choose. The materials are also important both in terms of the dielectric thickness as well as the decay value because those will determine crosstalk suppression or crosstalk reduction. Then the pads and the vias and the lands are all quite difficult to design because there are so many parameters. And so when you have a very high layer count board, like I've shown here on the right side of the screen, with several different thickness and dielectric options, and the dielectric is never constant all the way through the board, it actually switches between different values as you go from layer to layer, that then affects how these different parameters that I've outlined on the left affect the impedance and affect impedance matching looking into and out of the vias and lands. So just some of the parameters that we have. Obviously stitching vias, anti-pad size, via diameter, whether we're using blind and buried and staggered vias, or whether we're just stacking vias all the way through the structure. If you do happen to use through holes, whether or not you have a stub matters, and of course the stub size needs to be very small when you're at 56 gigahertz. The reason for that should be pretty clear. Once you are below 10 mil for these stubs, they're actually very difficult to fabricate with controlled depth drilling. And so that requires you either have very thin layers on the outer sides of the board and you're routing all the way through, or you're just using blind and buried vias all the way through the stack. So the reason this becomes difficult to work with in the design is because if I start to change one of these parameters in order to achieve minimal loss along these interconnects, it might require me to change at least one other parameter in order to prevent the creation of a new signal integrity problem at a different frequency. This is one of the reasons that we rely so heavily on simulation in designing these interconnects. It's because, of course, there are so many parameters, but also we need to get some sort of sense of how changing one of these parameters affects the loss in these interconnects. And that's not so intuitive. In some ways it's intuitive at some frequencies, but then there can be a switch to non-intuitive behavior at other frequencies, and changes in these parameters that are required to achieve impedance matching and minimal loss and reduce crosstalk are all interrelated with each other. Another issue arises with materials, as I alluded to earlier. So one of the issues with materials is with stable dielectric constant over broad bandwidths, and then the other is copper roughness. So anyone who is familiar with any of Rogers' technical data would recognize these two graphs. These graphs are from Rogers, and they are showing loss and dielectric constant consistency over frequency for two different types of copper. So the first is for their electrodeposited copper, which is the lossier of the two curves on the left, and then their very low profile electrodeposited copper, which is the less lossy curve on the left. Here you can see what appears to be somewhat greater variation with the electrodeposited copper versus the very low profile copper. One of the issues that arises here with these materials is, of course, simulating them. And so we have to leverage some either tabulated data or some standard model for understanding how copper roughness affects both the dielectric constant modification as well as the losses on the interconnect. So your simulation program needs to be able to handle these parameters, both the dispersion in the dielectric constant as well as the loss dispersion due to copper roughness. So in order to overcome some of these challenges, the workflow that we use to move through simulation-driven design is very important. And so this is one of the reasons that Altium and Ansys have come together to create a unified workflow that leads you from design into simulation and even into third-party applications and then back into the design. Getting feedback from the simulation is very important for the designer. The designer then needs to know how the design gets modified in order to then iterate through different possible options for these interconnect designs and then put them back into simulation so they can be qualified. So this workflow involving Altium Designer, Altium 365 as a cloud version control system, and then Ansys involves a push-pull workflow. And so anyone that has used MCAD collaboration tools should be familiar with push-pull workflows. Essentially, the designer in Altium Designer can push the design into Altium 365. The Ansys user can then pull that design into Ansys and then run whatever simulations they need to run. They can then generate reports. That report can then be passed back to the designer. The designer could then work in Altium Designer or in a third-party application to continue to optimize the design, and then this goes back into Ansys. So all of this is done without file sharing. So that's very important because anytime I've had to do this kind of simulation-driven workflow with a contractor or with a collaborator, it's always very difficult because you have so many files going back and forth between the front-end documentation telling the person what they need to simulate or what the settings should be, and then of course with the results going back over to the designer, and you have to keep track of all of it. So Altium 365 really helps with keeping track because there's a version control system. So the version control system is what allows you to keep track of all of the design iterations as well as the associated simulation results, and then you can recall those if needed, if you need to then roll back to an earlier version of the design. So let's take a quick look at how this works with a simple example. Now this workflow begins in Altium and it uses the standard push-pull workflow that we all enjoy from MCAD. And once you're in Ansys, you can then pull the exported project into Ansys. So all of this works without file sharing. You can then create a local project and then proceed to go into your analysis. Here we're just showing a simple power integrity application. First, we're setting up the analysis and then calculating the power distribution network impedance for several values of a placed capacitor. So the values are parameterized. Once the analysis completes, you can see here we have the results, and we can overlay all the results on top of each other. We can then see the impedance for different values of this capacitor and then compare. I'm sure everyone is familiar with this application. Once the analysis is complete and any problems have been identified, those can be called out as a comment, and we can then export those back to Altium via Altium 365. Also, Ansys will generate a report, as you can see here. And once those changes and the report are pushed to Altium via Altium 365, you can then go back into Altium, pull in those updates, so you'll be able to see the comment from the simulation user, and then you can access the generated report inside of Altium Designer. So now let's look at a simple example, and we'll see what kind of data we can get from this and how we can optimize this design. So here we have an example of a module land pattern on a PCB. Here you can see the differential pairs coming out from this module being routed vertically. You can see the antipad openings, and you can see the differential pairs through the pore on the top layer. So these are being routed as strip lines. Here we're using tachyon 100G dielectric. The decay is 3.02 or 3.04, depending on if you're looking at core or prepreg. We're using blind and buried vias. Staggered vias could also be used in the core layers. And then this design is targeting a 90 ohm differential impedance. So now when we put this through the workflow, we can get out, of course, S parameter data. This is the first place we would start to look at SI in these channels. Here we have the differential S parameter data. What you're seeing here is the return loss and the insertion loss in the red and blue curves, respectively. And then we have next infexed into a adjacent differential pair. So we have the near end crosstalk and the far end crosstalk. Now, we can already see just from looking at the return loss that the return loss is pretty high once we get into the frequency range where via impedance really starts to matter. So that's generally above about 3 to 5 gigahertz. And so we get above this negative 10 dB, and that high return loss is then reflected in the insertion loss. So we can tell that this channel is already return loss dominated. The crosstalk is reasonably low once you get into the 10 to 20 gigahertz range. However, once you get into higher frequencies, you can see that it starts to rise above negative 30 dB at several frequencies as you get to higher frequencies. So the first place to start to improve this channel is to look at the vias and the pads. So as I mentioned earlier, vias and pads are really going to dominate this return loss dominated behavior in short channels. So if we then go and cycle back into a third-party application, we can then look at the vias and pads, or we could optimize these in Ansys. Now, I prefer to use Symbior to do via optimization. I really like the interface. So this is an example where you can go back into a third-party application and optimize some aspects of your design. So here in Symbior, I've pulled up the old vias and the new vias. The old vias in the internal layers, they had the NFPs removed. However, you can see we have this really tight antipad around the differential signal vias. And then that really tight antipad creates this big capacitive dip at high frequencies, reaching all the way up to the bandwidth requirement for this channel. So if we just change this antipad, we could then improve the impedance looking into this via. And that's what I've done here on the right. But just by doing a little bit of rearrangement on stitching vias and then opening up this antipad, we are then able to bring the impedance much closer to the target impedance of 90 ohms all the way up to our bandwidth requirement and a little beyond that as well. So once we do this, we can then take this information, update it in Altium Designer, and then once we have the updates applied in Altium Designer, we can send this back into Ansys for further analysis. So the change in the vias is of course going to be reflected in the via S parameters. So this is something you can do on the front end just to verify that your proposed design change is going to work. Here we can see the old vias. They were indeed reaching above negative 10 dB once you get to those higher frequencies. And then once you get over to the new vias, you can see that they are well below negative 10 dB. You see an improvement in the eye diagram as well. Now, this doesn't totally explain what's happening at the lower end of the frequency curve. However, if you just look back here at this slide, this is just one of the vias in the stack. There are other vias in this stack that would also need to be optimized in order to fully address the entire frequency range for this interconnect. So we would also need to look at the other vias in this stack as well. So what else can we do here once we are working in this kind of workflow? Well, the other thing that we can do is, of course, extract touchstone files for the various portions of our interconnect. We can then extract a PCB model. We can take a package model. If we can then put those together into a 3D model, we can then do full linear network analysis for an end-to-end workflow. So we can take all of that information, use it in a larger cascaded model, and then with this new model we can then predict the S parameters for this new network before we then go off and do a new physical design. Now, earlier I mentioned that the package also matters for these types of systems. So I want to briefly address some of the package challenges because, of course, the package has to meet the PCB and they have to work together to ensure that the system is going to work to spec. So your PCB could be designed perfectly, but of course if your package is incorrect, then the channel may not function. So the first aspect of channel design that's quite important is the BGA pitch and size. These together determine the quasi-TEM cutoff frequency. So when our ball pitch gets smaller, we generally have a higher cutoff limit for the quasi-TEM mode. And we would like for everything in the system to operate in the TEM mode. So that's everything inside the package, and then the transition into the PCB, that signal launch, and then the interconnect inside the PCB also need to all operate in that TEM limit. The next aspect of the package that's quite important and relates more to the material aspect is the substrate decay. So when the substrate decay starts to get lower, it actually reduces our tap length requirement for equalization. This data was taken from an Intel working note. You can see the citation down here on the bottom. So anyone that's interested in this data and some of the work that they did, I'd encourage you to check out this paper. Going a bit deeper into the package challenges, we then have the ball out. The ball out is very important. Here you can see on the lower left, I have an example ball out. The blue dots represent ground connections, and those are being used to isolate TX and RX connections into the package, and then the red arrows indicate the routing direction. So here the connections to ground like this are essentially being used to isolate these channels vertically. So this is meant to address via-to-via crosstalk. Once you have the ball out arranged like this, not only do you impact the via-to-via crosstalk, but this also allows you to route your RX and TX on different layers so that they're further isolated from each other. This also forces you to have your TX lanes to be very largely separated, and that large separation also helps to reduce crosstalk. One of the other things that's quite important is group delay dispersion. If we can maintain low group delay dispersion, then we're going to have low ISI. So one of the rules of thumb is below approximately 1 picosecond group delay dispersion, up to as high frequency as possible, and that will help ensure low ISI. This is also related to the ball out and the ball pitch. The other thing that we need to worry about is die package PCB end-to-end modeling. So how can we build these full models that really address all the possible sources of loss in these systems? Also, the modeling of them is very important in terms of how they relate to frequency and then the geometry of the system. So we have the skip layer routing losses, which are proportional to V over D, where D is the distance between the internal traces and the upper and lower planes. Then, of course, dielectric and copper losses are proportional to frequency and the square root of frequency, respectively. And then we have the issue that I mentioned earlier with dielectric constant. Is it really a constant? I think we all know that it isn't actually a constant, and then that needs to be included in these die package PCB models. So the final point I'd like to leave you all with is, what will be the next data rate doubling? So will we just double the Nyquist rate, or are we going to use alternative modulation? So Keysight, in a February 2023 blog post, did bring up the possibility of PAM6 or PAM8. So 448 gigabit per second PAM8 would look something like this, where we have 8 signal levels, essentially transmitting 3 bits per UI, and then that would give us a 149.33 gigabaud bit stream. Then that would set the Nyquist at 74.67 gigahertz. So on the optical side, there's already some work in progress. An example is right here, as I've cited. In this example, they are demonstrating 448 gigabit per second PAM8 transmission over multi-core fiber. So I expect to see more of these demonstrations in the future, and we will see what the modulation technique comes out to. Thanks everyone for listening, and you can contact myself or Altium Enterprise Solutions to learn more.